All right. Good afternoon, ladies and gentlemen. Today we're going to be talking about fuzzy matching. So, fuzzy matching is going to be an important topic that we're going to be covering for essentially the rest of the semester. But what I wanted to do, first of all, is to introduce several concepts. First of all, what we're going to be talking about today is we're trying to answer three questions. First of all, what is fuzzy matching? Why is it important? And why do we need to care about it? Why can't we use our existing techniques, the hash tables, the binary search, things like that, to solve the problem of fuzzy matching? Why do we need to develop new algorithms for it? And finally, how do we define or how do we threshold how fuzzy of a match are we willing to get, right? So let's begin. First question, what is fuzzy matching? At its most basic, it is just the ability for us to identify things that are similar to the query that we're looking for, right? So our goal with fuzzy matching is to identify strings that are similar to our query. So there's a couple of things that we're eventually going to need to define. First of all, how similar do we want our targets to be in order for us to be able to find it? And second of all, how are we going to go about doing it? So the reason why it's important, for example, if you type something into a Google search bar and you're off by a couple of characters, let's say you're looking for, I don't know, your favorite store, and then you misspell the name of the store. Google is still going to find the thing that you're looking for. It's going to ask you, hey, were you meaning to say this, right? So we want to be able to not have our algorithms completely broken by one or two misspellings, right? Because humans make mistakes. And in our data sets that we're talking about here, which is specifically text matching, genomic matching, we want to be able to tolerate some error in measurement and still find the thing that we're looking for. So if fuzzy matching is just about finding things that are similar enough to the thing that we're looking for, why can't we use our existing tools, right? So let's say, for example, we have our, so why can't we use previous algorithms? So if you recall, the problem that we're trying to solve in this class can be defined as this. We have some large number of queries, big N. We have some large data set, in our case, it's genome, it could be any other big text. And we're trying to find the existence of a queries in subject. So let's say I have a query that is ATGTAC, right? And I do not actually have that query inside of my subject. But what I do is ATATAC, right? So these two are different by a single character. In order for us to use our perfect match tools, that we have previously developed, such as the binary search in arrays or hash table based searches. We're going to have to do something special. So first of all, can we find this query inside of our subject if it's got one error in it? Well, the answer is no, we will not be able to find it. In the case of binary search, just that single character makes the word different enough for you not to be able to match it. In the case of a hash table, things are even worse because you will probably have to convert this into a radix value, and that radix value is going to be significantly different because of these two characters being different. So if we did want to use our existing tools to solve the problem, one of the ways that we could try to go about is we could try to store in the hash table every single permutation of every single query that we were looking to find, right? So if in our hash table we are storing the queries and then we're going through the subject to search for it, that means that for, let's say, our big N is 27 million, like in your homework assignment, and let's say our little n, the size of the query, is 36. If we wanted to introduce every single possible one character away sequence into the hash table that we're storing, instead of our hash table containing O of G, or 27 million fragments, our hash table would actually have to have O of G times 36 times 4, right? That is assuming that we are willing to convert every single one of these characters to 4 different possibilities, right? So if the character had A in the first space, we would have to consider C, T, G, or N. Same thing for the second space, same thing for the third space. As you can see, the problem with doing it this way is it makes our fairly large hash table already much larger, right? But not only that, but that does not really solve our problem, right? The reason it doesn't solve our problem, what if I tell you that we need to be able to tolerate 2 errors? Introducing 36 choose 2 errors into every single one of your queries becomes cost prohibitive. What if I say I want 3 mismatches? So as you can see, our existing tools are just not going to work, right? Our existing tools that we've been talking about in this class have been designed to work with perfect matches. Okay, so if our existing tools are not going to work, let us define some distance matrices, right? Because if we're going to be developing new tools and new algorithms, we're going to need to figure out how close is the match that we're currently looking at from the target sequence that we wanted to find. So let's introduce several of these. So 3, what about? So what about the metrics? So in this class, we're going to be, over the course of the semester, talking about several different types of distances. The easiest one to understand is the Hamming distance, right? That is the minimum number of substitutions only, no insertions or deletions, we need to use in order to convert one string into another. So right? So in the Hamming distance, if we have a word bat and a word cat, the Hamming distance in this case would be 1, right? Because all we would need to do is convert that B into a C, and we're good to go. If we have the word bat and let's say bit, again, 1 character conversion converts 1 word into another. It does not really matter where that word is. Now, what happens if I have 2 words of different length? Well, as it stands, there is no way for you to, in the Hamming distance, the way that we've defined it here, there is no way for you to convert it into bit. Because in order for you to do that, you would either need to insert a character, B, or you would need to delete a character, B, right? So in this particular case, as you can see, it's great for defining distances between 2 strings of the same length, not so great when you're trying to deal with words of different length or situations where you want to introduce or remove characters. So that brings us to the modification to the Hamming distance called the edit distance. And the edit distance is very similar to the Hamming distance. The only difference, of course, is instead of number of substitutions, we're talking about the number of operations. Insertions, deletions are okay to convert 1 string into another. So, number of operations. Allowing insertions and deletions, right? So in our previous example, when we had bat or cat, the edit distance is still 1, right? Because all we really need to do is do 1 substitution. In our other example, when we had bit and it, the distance is also 1, because all you would need to do is delete, for example, this B, and the 2 words are the same. Interestingly, it allows us to consider situations like this. So let's say in my genomic example, I have this string, and I am looking for the distance from this string. In the Hamming distance, these would be actually very different strings, right? Because this would need to get changed, this would need to get changed, this would need to get changed, this. So the Hamming distance here is 6. Now, the edit distance, I'm going to argue, is 2. All I need to do is shift this whole thing to the right 1 character, and these 2 are identical, right? All I need to do is introduce a gap here and introduce a gap here. Okay, great. Now, this is a good way to determine how close or how far away 2 string fragments are. But in my previous example, when I used the example of you typing something into Google, you are probably not going to make completely random errors, right? So if you're trying to type the word, I don't know, bat, you might write the word hat. right? Because B and H are close on the QWERTY keyboard. So how do we deal with a situation where we want to assign certain weights to different types of errors that we would have? So, for example, let's say I think it's more likely that I'm going to make a substitution, change one character for another, rather than insertion where I randomly start adding characters. I would much more likely make a consonant to consonant error versus consonant to vowel, right? So this is where the similarity score comes in. And a similarity score, rather than the number of operations or the number of substitutions, allows you to use weights to score similarity between two strings. So there's a couple of things that we want to introduce here. First, let's talk about the similarity matrix. So we're going to be using this a lot in this class. And let's say we are in the genomic example that we've been using throughout the class, and our alphabet is A, C, G, and T, right? So what I'm going to do is I'm going to define a matrix that's going to store what the different scores for me are. So let's say I want to, every time I have a match, I want to add +2 to my overall score, right? Now, is there anything stopping me from making the match of A to A +5 and a match of C to C +2? No, not really. You have to use the weights that make sense, right? And let's say every time I have a mismatch, I would introduce a score of -1, right? So great. So that handles substitutions. How are we going to handle deletions? Well, let's say I'm going to introduce a gap score, G, and every single time I have a gap, I'm going to subtract 3 from my overall score. Now, this will allow me to take two character sequences. Let's say we have sequence 1 is, let's say GAT, CT, GATTA, right? We're going to be using this sequence several times in the upcoming lecture. And the sequence 2 is GC, TG, ATTC. So several things I want you to notice. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 characters here. 1, 2, 3, 4, 5, 6, 7, 8. 8 characters here, right? Great. So if I wanted to compare two possible ways to match up these two sequences, let's say I'm going to want to compare GATCT, GATTA, and then G gap gap, C, T, G, A, T, T, C, right? What would be the similarity score for this particular element? So +2, -3, so that would be what? -4, -2, 0, 2, 4, 6, 8, and then a mismatch. So this would give us a score of 7, right? Now, let's say I want to consider another possible way to align those two sets of strings. So let's say we do G, A, T, C, T, G, A, T, T, A. That's my sequence 1. And I have G, C, T, gap, gap, G, A, T, T, C. What would be the score here? So +2, because we have a match. Mismatch here. So +2, 1, 3, 0, -3, -1, 1, 3, 6, 7. Great. So this is another possible way to align these two sets of sequences that gives us the same score of 7. So where I'm trying to get at, eventually, if we want to be able to provide any sort of a guarantee, whether or not we found the best possible fuzzy match that we could find, we're going to have to compare multiple fuzzy matches. And now we have the arsenal to do that. We can either use the Hamming distance, which is just number of substitutions. Every single type of substitution has the exact same score, +1, or in this case, actually -1, because it's a dissimilarity matrix. Edit distance that accounts for insertions and deletions, and finally, similarity score that allows us to assign weights to the type of matches that we want to see and penalize the type of things that we don't want to see, such as, for example, mismatches or gaps. Okay, so great. We are going to be using this later on to start talking about some of the algorithms that will allow us to do fuzzy matching. Thank you, and I'll talk to you all soon.